Now, we just discussed this formula, which, again, ladies and gentlemen, is the formula of a normal curve. Probably didn't discuss that when you were in probability and statistics, but every normal curve, every situation that fits a normal curve probability situation can be modeled by this function. All you need is the mean and the standard deviation, which are the two things, if you had probability and statistics, that you dealt with, is the mean and standard deviation. You take those two things, plug them into this formula, and simplify, and you've got your normal curve function. Now, just a couple things, not overly relevant to what we're doing, but if you are just curious about normal curves, you do know that 68% of the area lies within one standard deviation of the mean, 95% within 2, and 99.7% within 3 standard deviations. And it's considered that basically nothing ever lies outside of that 3 standard deviations of the mean. Alright, our last problem. Weights of spinach boxes. Yum, yum. We all love spinach so much. Actually, that's a lie. I don't. I hate it. Alright, you have frozen spinach boxes that are marked as 10 ounces. The mean weight of the boxes is actually 10.3 ounces with a standard deviation of 0.2 ounces. Now, mean, you know how to find mean. If you want standard deviation, you have to go talk to Mr. Rowland. Very long formula. Don't remember how to do it. I'd have to look it up. But essentially what standard deviation is on average, how do the actual weights of the boxes differ from the mean? So the average of the error, if you will, is 0.2. Assume the weights are normally distributed. A, what percentage of the boxes can be expected to weigh 10 to 11 ounces? B, what would we what would we expect to weigh less than 10 ounces? And then C, what's the probability that it weighs exactly 10 ounces? Apologies, ladies and gentlemen, I'm coughing all over the place here. First of all, we need to come up with our function. Here's our function from the previous slide. We need to plug in our standard deviation, which again is the sigma, and our mean, which is the mu. Standard deviation was 0.2, so that goes there and it goes there. And the mean, mu, was 10.3, so we put that there. And we can simplify that just a bit. 2 times 0.2 squared is 0.08. Now, part A. Percentage of all such spinach boxes expected to weigh between 10 and 11 ounces. So I take the integral from 10 to 11 of our function, our standard, our normal function. Certainly would be insane to work that one out by hand. Plug that into your calculator. 0.933. So you have a 93.3% chance of the boxes weighing between 10 and 11 ounces. Alright, the next one says less than 10. What percentage do we expect to weigh less than 10? So that would be 0 to 10. We'll plug that into our calculator and we'll end up with 0.067. So a 6.7% chance only that it's going to weigh less than 10, which makes sense because if you add these two up, that would be 0 to 11. That's nearly 100%. Remember, we talked about how it's not going to go more than a certain number of standard deviations out. What about the last one's interesting. What is the probability that a box weighs exactly 10 ounces? Well, between 10 and 11 we went 10 to 11. Less than 10 we went 0 to 10. So exactly 10 ounces we would go 10 to 10. And I don't even have to punch this into my calculator because I know that if I'm starting at 10 and ending at 10, the answer is 0. Now, does that mean it's impossible for it to weigh exactly 10? And, you know, impossible is kind of a crazy word, but if you consider all the possibilities that it could weigh, you know, you say, well, this one weighs exactly 10. Well, does it? Or does it maybe weigh 10.0000, you know, 1,000 zeros and then a 2 ounces? You know, to get that exact weight of 10 is near impossible. And this is where Mr. Myers and I didn't always agree, but we do agree on this point. You know, he always talked about how we lived in an imperfect world and there were never any perfect measurements. And to get a perfect 10 ounces with 0 error whatsoever really would be impossible. And if you ever have something that's exactly 10 ounces, I would tell you to measure more accurately, because perhaps with a more accurate measurement you would see that it's not exactly 10 ounces. And that, ladies and gentlemen, is the end of Chapter 7. We'll work on this tomorrow and then start getting ready for your AP and test review.